Okay, so we were talking about the thrust required concept. I hope you remember that. So I'm going to make a detailed review of our last lecture, and then I will continue from there. So it was last Tuesday, right? We were talking about, we started writing the equation of motion. So there are two equations involved in terms of aircraft performance for longitudinal flight. So these are two force equations, one for the forces that are parallel to the direction of flight, and the other is the equation for the forces perpendicular to the flight path. As in the most general case, there may be some accelerations involved. So these two equations you see here include those equation terms. And then from these most general equations, we returned back to our steady level flight condition. We make certain assumptions, and after these assumptions, okay, so you see there are some simplifications introduced. The acceleration terms just disappear, and then these angles disappear as well. And in the end, we get these two simple equations. And so these two equations are actually very simple, but they're also important as well. So for a very big, for most aircraft, a very big part of the flight takes place under these conditions. Okay, so if you study the performance for these conditions, then for civilian aircraft especially, your result will give you the overall performance very closely. Okay, and then after that, there are two aerodynamic forces here, the lift force here and the drag force here. And these two equations, the forces are related through the drag polar equation. Okay, so if you write the drag and lift equations, these two equations here, then you can connect these two equations if you use this relation here, which we call the drag polar equation. Okay, then there was this example. Okay, so by using those, using the relation between the lift and drag coefficients, you can combine these equations, and in the end you get a single equation. Okay, so this is the drag equation, the aerodynamic drag equation, which we also call thrust required. So you see a single equation here, but it actually includes the effect of two equations. Okay, so if you look at the term here, this comes from the other equation. So let me just mark that as well. So it comes from the weight is equal to lift equation. So you combine two equations into a single equation. And then for this single equation, I showed you some plots and an example. Okay, so I gave you this example, and we calculated certain parameters for this aircraft under a steady level flight condition. First, I said that let the aircraft be flying at this speed, and for that we calculated the two components of the drag force, and then we made the calculations for another speed level, which was 50 meters per second. Then for the new speed, you calculate again those things, the induced drag component, the parasite drag component, and you can do this a lot of speed values, right? And you do that for within a certain speed range, you can generate some plots, and you see those plots here. For example, let me see. Here you see the lift coefficient value at different speed values. So if your aircraft is flying slowly, then you need a large lift coefficient to be able to carry the weight of the aircraft. But as the speed of the aircraft increases, the required lift coefficient value decreases naturally. So in this plot you see that. And for the drag coefficient, you can create a very similar plot. You see the two components of the drag coefficient and the total. The CD is the sum of these two coefficients, CD0 and CDI. Let's see. Then you can also make a plot of CL versus CD. That plot looks like this here. So these are the non-dimensional coefficients, and also you can make similar plots for the dimensional values. Okay, so if you plot the drag force, the dimensional drag force, not the non-dimensional coefficients, then you get these this curve here. So again, the red and blue ones are the components of the drag force, and the total drag force is the black one. And we also call that the required thrust force, right? Okay, so let's come to this, the thrust required concept. So let me copy this graph here and put it here. So this is a very important graph, and a lot of performance related calculations are made based on this graph. So this is actually the drag force, but we call it required thrust, because if you want to be able to make a steady level flight at this speed, for example, this is the drag force for that flight, and your engine should provide the same amount of force such that the equilibrium flight can be possible, right? So this is also the thrust required. So instead of drag, we can also call this, let me just write here, T sub R for required thrust. Okay. And so let me color these so that you can easily see which one is which. So there are two components here. And if you look at the first one, in the first term you have V squared term. So naturally this gives you an increasing term with speed. So this corresponds to this blue curve here, right? So it increases with the square of V infinity. So let me just make this blue. In the second equation, you have V squared on the denominator. And this has an inverse relation with V square, and that is shown in red in the graph. And the total thrust required is the sum of these two, which gives you this black curve here. Okay, so if you look at this black curve, you see that it makes a minimum somewhere, right? So if you fly at the right speed, which is this speed for this case, then the drag force or the required thrust force is the minimum. Okay, so your engines will need to provide a very small, well, the smallest possible force for that aircraft. But if you fly just a little bit faster or a little bit slower, then you need to provide more thrust force. So obviously this is a very special point for an aircraft. And so this is a very important point, and we need to know what this point corresponds to, right? And if you want to find that out, you can go back to the equation. So we are looking for a condition at which this point will be achieved. Okay, so before that, let me show you something and let's discuss on that a little bit. Okay, so I said that this graph is really important and we will be doing our calculations based on this graph. So let's think about that a little bit. Suppose that we have an aircraft, and for this aircraft the thrust required curve is given as this one here. Let me call this TR1. And there's the second aircraft, and for the second aircraft the thrust required curve is this, let's say. And let me change the color here. Let this be R, and let me call that TR2. So again, these are for two different aircraft. Okay, and so which one of these aircraft do you think is a better design? So which one would you prefer to have? Well, in terms of operation costs. Blue or the red one? Red one, right? Obviously, the red one is a better design. Why? Because the required thrust force is smaller compared to the blue aircraft. So if you have if you fly with the red aircraft, to be able to fly at the same speed, you need less thrust force to fly the aircraft, which means you need to burn less fuel. So obviously, the red aircraft is a better design. So where are we? So anyway, so this point is a very important point because it gives, from the graph you can see that this is like the best point, right? So at that point you have the thrust force you require is the minimum. And if you want to find out where that point corresponds to, again, you can go back to the equation and you can analytically find the minimum point of that curve by taking derivative with respect to the speed. So what you do here is this is the drag equation, which is also the thrust required equation. And as you see, that is a function of the speed, obviously. So if you differentiate this equation with respect to speed and equate that to 0, that will give you the point where the slope of that curve becomes 0, which is the minimum point here. So let me come back here again. Well, you can do that. You can take the derivative of this equation with respect to V infinity and find that point, or you can do something simpler. And to be able to do this simpler approach, what you do is you first write the drag force as this. This is the aerodynamic drag equation. And remember, this Q infinity is the dynamic pressure, which is equal to 1 over 2 times rho times V square here. And you write the second equation, or the first equation, the lift equation. So from the first equation, instead of Q infinity times S, you write weight divided by CL. And then you put that instead of this Q infinity S. And from there, you see that the thrust required can be written as the weight of the aircraft divided by CL over CD. And from here you can conclude that since the weight of the aircraft is constant, the thrust required changes with lift to drag ratio. And if you want the thrust required to be minimum, then you need to make sure that CL over CD is maximum. Okay? Now let's go back to the these curves here. So from the graph, we see that the minimum point for thrust required is this point, and this point or this speed is the same speed as this speed here, where the CL over CD ratio becomes maximum. Okay. O kadar çok git gel yapıyorum ki benim bile başım döndü vallahi, siz umarım takip edebiliyorsunuzdur. Okay, so to find this minimum point, so at this point, which is this, CL over CD is maximum. And again, these two are not independent. So instead of CD, I can use the direct polar equation, which is CD0 plus K times CL squared. And I think that was the last thing we did last week, right? And finding the maximum of this point, this time we take the derivative with respect to CL, and from there, the derivative of this expression with respect to CL is this expression here, and then you equate that to 0, and that equality gives you this condition. So CD0 should be equal to K times CL squared, but K times CL squared is the induced drag coefficient. So that means the induced drag coefficient should be equal to the parasite drag coefficient. And if you can find that flight condition, then that means you are flying at this point where the thrust required is minimum. So the maximum is obtained when KCL squared is equal to CD0, and this is equal to the induced drag coefficient. So let me just add some explanation here. So if you know the parasite drag coefficient of your aircraft, then you can say that you require thrust force for a steady level flight is achieved when CDI is equal to CD0, and hence the total drag coefficient is equal to twice the parasite coefficient, and that's because your CD0 is equal to CD0 plus K times CL squared, but your K times CL squared should be equal to CD0, and this is 2 times CD0. Okay. Okay, so let me just say that in most cases you measure CD and CL coefficients wind tunnel and obtain the drag polar graph experimentally. So you make a test and you measure the lift and drag force, and from there you find the coefficients and you put them here. You make another test, and let's say you obtain these results, and you keep repeating all these tests, and let's say you measure something like this. Okay, I'm just making it up. And let's just okay, so this is what you obtained experimentally. So when you have such data, you can find CD0 value and then find the drag coefficient for the condition, or you can find the drag coefficient for minimum thrust required directly from this graph. Okay, so I have this graph, right, and I'm looking for the condition at which this ratio is maximum, right? The CL to CD ratio is maximum. And this is the origin. So let me show you a graphical way of finding that special point. So let me use the green color. So let me draw a line from the origin to a data point here. So let's say this is, let me choose this data point. And if you draw a straight line from the origin to that data point, you get this line. And this is CD, let me call that CD1. Let this be CL1. And the angle of this line with respect to the horizontal axis, let me call that theta. The tangent of theta is CL1 divided by CD1. Right? So again, I drew a straight line from the origin to a data point, and if I look at the angle that line makes with the horizontal axis, that angle, the tangent of that angle is the ratio of lift coefficient to drag coefficient. Okay? So now can you tell me when this ratio becomes maximum? So for this ratio to be larger, the angle needs to be larger, right? So for example, for this data point, the ratio is larger, right? Because the angle is a greater angle, right? The angle for this case is larger. And for this case, the angle is more or less the same, but just a little bit larger. If you do it for this data point, the ratio is smaller again, right? Because the angle is smaller. And the angle is maximum when this straight line becomes tangent to this direct polar curve. So how should I say that? So this is, so in this case line is tangent to the CLCD curve. Theta is maximum here. Which means CL over CD is maximum. Okay, so were you able to follow? So this is a very quick and easy way to find that special condition, and you may get a question like this in the exam. So I can, for example, give you a data like this, and then I ask you to calculate the minimum required thrust point. So what you can do is you can quickly draw a straight line from the origin to that point. So for example, for this data, this gives the so let me call this CD star. So it really got really messy here. I don't have too much space left. So from the CLCD data, we conclude that at the minimum thrust required point, CD value is CD star, and naturally the corresponding lift coefficient value is can also be found from here, and that is this value here, and this can be called CL star. Good. So is this point understood? Because we will be doing this again. So we will be doing the same concept again to find other important points. So I'm talking about this, drawing a straight line from origin to a curve. And hopefully this point is well understood. So if you draw a line from the origin to this point on this curve, you have this much CL over CD ratio. But if you draw it from here to another point, for example, for this point, then you get a larger angle, which means you have a larger CL over CD ratio. If you draw it from here to here, then the angle is very small, right? The lift to drag ratio here is very small. And you're interested in the highest possible lift to drag ratio. The highest possible lift to drag ratio means highest possible angle, and the highest possible angle is obtained when this line becomes tangent to this curve. Okay, so as I said, we will be doing the same thing again for finding different things. So it's important that you understand why we are drawing this tangent line, because the angle is maximum for the tangent line. Okay, so if you have obtained the data experimentally, again, you will do this in the wind tunnel. So once you have collected this data, you don't need to worry about calculating CD0 first. You can just find the minimum point by just drawing a tangent line, and that from tangent line you can say that this is the drag coefficient value for the minimum TR point, and this is the corresponding lift coefficient value. And the ratio of these two values is the highest lift to drag ratio for your aircraft. Okay, so let's continue from here. So what you see here is actually the same thing. So what I explained here, this was explained previously last year, and the notes for the last year is written here, so you can see that this is how I explained it last year. Now let's go back to the drag is equal to TR equation. Let's make it all black. Okay, so we have an equation which is a function of speed, v square here. So let me just arrange the terms a little bit. So let me just write it one more time. Let me call it TR is equal to 1 over 2 times rho infinity times S times CD0 times V infinity squared plus okay, so I didn't change anything. I just changed the order of the terms a little bit. And let me call V infinity squared X and let me call, if I can use red color for this. Let me call this A, little a, and let me call this TR minus B, and let me call this part C. Okay? Now you will soon understand why I call them that. So if I do that, I can write this equation again as minus B is equal to A times X, because I call this X, plus C over X, right? So if I multiply this equation by X, that will give me AX squared plus BX plus C is equal to 0, right? And I know that this is a quadratic equation. It's a second order polynomial in X, and which that has two roots, and I can tell you what those roots are from the following relation. The roots of this equation are x12 minus b plus minus 4ac divided by 2a. That doesn't look very much like a 4, so let me fix that. Okay, so you know that, right? You know this relation, the two roots of a second order polynomial? So I can go back and insert A, B, and C into that equation. Okay, I'm just too lazy. I will just copy it directly from here. So these are the two roots for the x, but remember x was the square of the speed. So we basically found the square of the speed. So what you see here is obtained from here by inserting A, B, and C. So if you put this for A and minus TR for B and this for C, you get this expression. And you can modify this expression slightly to obtain this expression, V infinity for V infinity. And do you know what we did here? I mean, what this V infinity corresponds to? And there are two roots, remember. So this can be a plus or a minus, and both of them will give you the roots to that equation. So we still have the plus minus sign here. So you can add or subtract this term from here or add to that, and then the what you get will still be a solution. So what we found there are the two solutions that I'm going to show here. So if I choose a required thrust value, let me choose this as my required thrust value. Let me call this TR1. And I equate my direct equation to TR1, then you see that there are two solutions here. And these two solutions you see on the graph are given by this equation here. Okay, so it's time for a break. So let's give a break and continue after that, okay? So I feel like it was really too much to explain in one lecture. So let's just give a break, and after the break, hopefully it will be easier to follow.